Hey, did you see the topic? I think what is it?
It's splines.
No, I think it's splines.
Did you read?
I read. I think it's Long I.
What? No, it's
Splines.
no, it's spleens.
Splines.
I read and it's
Spleen spline. Guys, it's the topic.
Welcome back, Bio 6618. In this lecture, we'll talk about an introduction to splines and their use in linear regression modeling. We'll first introduce a motivating example to use to explore the world of splines and how we can model them using our statistical software. Let's start with that motivating example. Now let's assume we're interested in the association between sex hormone binding globulin, or SHBG, and age in years for males who are 6 to 80 years old from the National Health and Nutrition Examination Survey, NHANES, from their 2015 to 2016 cycle. And we see here we have a pretty decent sample size of 3390 that have this outcome. Now, just looking at this pretty dense scatter plot of all of this data, we can see that there appears to be some sort of non-linear trend in the model. So you might want to explore how we can model that and account for its sort of true nature. One strategy that we've talked about a lot in class is using simple linear regression. So we see here on the plot we've added a linear regression line, and we see that it just doesn't fit the data very well. For example, at younger ages there's a whole bunch of higher values than we would expect. And then in this middle area of the graph too, it seems like most points are below it. So it seems like there's something to be desired from this simple linear regression fit. Now, one strategy we have discussed so far this semester is polynomial regression. In other words, including higher order terms of x. So not just age, but maybe age squared or age cubed and h to the fourth. Now, we see here on the plot below, we have an example with a squared, cubed, and quartic term added to the model. Now, we see that it looks better definitely than the simple linear regression, but there's still some concerns. For example, the red order 2 model fit there might actually be underfitting the data still, better but not great, whereas order 4 may have a little bit of potential overfitting. And likewise, order 3, we aren't sure if it's quite the best fit. So we might be looking for something still that might be a little more flexible. For example, we may wish to use something like a polynomial spline. And this is a more flexible alternative to polynomial regression that we're going to explore in greater detail in this lecture. We can just see in the graph here alone that we've added an example of what are known as B-splines and natural cubic splines. And we see that while they're fairly similar, they do have a little deviation or shift from their distributions, and also relative to the order 3 term, depending on the degrees of freedom we set in these terms, we can get them to have different shapes. So with that motivation, let's take a look at actually some types of splines and some of the technical details behind them. Generally speaking, splines allow us to mathematically reproduce flexible shapes. The big thing here being that reproducibility. So we can come back to, let's say, our data set or future problems and recreate the process. Now, in linear regression, splines provide flexibility to model our continuous predictors that have nonlinear trends, or ones that we've explored previously that we thought might be candidates for polynomial regression. The concept here is that we place knots at several different places along the range of x, with adjacent functional pieces joined together. In other words, we're trying to provide some sort of almost flexible range of values with separate micro or local models fit between them. Now, to be fair, there are many types of splines. But in this lecture, we're just going to introduce and focus on B-splines and natural cubic splines. The type of polynomial and number and placement of knots is what will then define the type of splines that we explore. So let's start by motivating splines more generally from polynomial regression. So we see in polynomial regression, if we have our order 3 model, what that really means is that we have x squared, and x cubed in that model. Now, we can similarly think of these actually as u squared, and u cubed here, where u is a function of x called the basis function. In the case of polynomial regression, we can also represent this as a matrix, as we see below here, where we have a vector of 1s for our intercept, and then our 3 terms ui squared, and ui cubed in matrix notation. carrying this forward, we can also generalize this even farther to note that y can be shown to be equal to something more generic like f of xi plus epsilon, where f is some function or transformation of the predictor. Now, one of the reasons we're looking at splines as an alternative to polynomial regression is that they have the issue or potential limitation of non-locality. This is the case where data fitted across a regression line at any arbitrary point we'll call x naught ultimately depends on the data across the entire range that we're fitting. This means that changes in the observed values near the boundary, such as the minimum or maximum value we observe of x, can actually lead to pretty large changes in our fitted function even far away from that value, which may cause issues or drastic changes in our estimation with subtle ultimate changes in the data. Now, as an alternative here in this lecture, instead of fitting a global polynomial over that entire range of x, we can partition x with those knots, which we're also going to denote with the Greek letter lowercase tau. And we can fit localized polynomials within and between these knots. This is really the general motivating concept behind splines, that we can divide our range of x into smaller subunits or ranges of values and fit models on those sort of local sets of data. Now, if we define a set of knots that say tau 1 up to tau k over the range of x, our spline f of x will ultimately look like a smooth function of polynomial of some degree d that we can set. Now, we actually have a lot of power to obtain increasing flexibility in our curves by either increasing the number of knots we have, so more and more local fits, and or the degree of the polynomial. But we do have to be aware of this idea of the bias variance trade-off appearing in this decision. For example, if we increase that number of knots and or the degree of freedom too greatly, we actually might overfit the data and therefore increase our variance. Likewise, if we choose too few knots or decrease the number of knots and or use a low polynomial degree, we actually might still poorly fit the data and increase our bias, much like that linear regression example we saw before. Now, the next few slides introduce some of the technical details underlying the code we're ultimately going to leverage in R. For example, we're starting with the B-splines. This is a common type of spline basis that can be fit in R using the code we see here from the splines package with the BS function. Now, ultimately, the B-spline basis is based on the following knot sequence. We've added some color coding here to try to tease apart these different pieces. You can note here we're representing these by various forms of C. And so we can see that the inner knots are represented by our blue colored ones. And we can also denote this as tau 1 to tau k, that 1 to kth knot that we're interested in for fitting our splines. In red are the boundary knots, which we can denote as A and B. And then the choice of additional knots, all the black colored knots located above or below those boundary knots, are ultimately arbitrary, and many common strategies are to set them equal to those boundary knots. Now, the reason we have so many knots in different ranges here is because in the B-spline basis functions of some degree d, which we can denote more generally by this capital B sub k superscript d of x, they're defined by the recursive formula you see on the screen here. Now, it's somewhat complicated, so we don't spend too much time actually focusing on the details here, but you can note that it has this idea that within the B sub k, we are looking at the idea of having different k and k plus 1 terms incorporated. Now, within this as well, we see we have this idea of sort of an indicator for bk0 of x. And it does equal 0 if, let's say, our terms are k is equal to k plus 1. Now, building off of that idea, what we'll see implemented in practice in a moment is also the idea of natural cubic splines. Now, these are like the B-spline, but has been noted performance that the B-spline itself has no limitations on the behavior and the boundaries of your data. So it can sometimes be a little erratic. To address this limitation, natural splines represent cubic splines that have additional constraints that the spline is linear in the tails of the boundary, or in other words, that negative infinity to A or B to positive infinity range. This constraint is ultimately achieved behind the scenes by requiring our spline function f to satisfy that both the second and third derivative are equal to 0. This requirement ultimately leads to 4 additional constraints that a natural spline basis on k knots will have k plus 1 degrees of freedom. Now, with some of those technical details out the way, you might be wondering, cool, this hopefully will look really interesting when I fit my data, but how can I actually interpret it? And the unfortunate news is that there's a similar challenge to polynomial regression, that it's not really easy or intuitive to interpret the beta coefficients that you ultimately are estimating. Now, if the spline is applied to our primary explanatory variable of interest x, it may be the most advantageous to actually focus on graphical summaries of the data and overall tests of the contribution of this model relative to a simpler or more parsimonious model, or alternatively to fit specific combinations of our predictors to get predicted values for y and potential confidence intervals. However, if you're using a multiple linear regression framework, you actually might be using splines to more flexibly adjust for other variables that are in the model outside of just the PEV. In this case, if your PEV is just, let's say, its own variable without any transformation, we can still interpret that variable the same way we do that a 1 unit increase in x of the PEV results in an average change of beta hat PEV in our outcome after adjusting for all other variables in the model, even if those other variables are fit flexibly with splines. Now let's dive into a brief example in R and some different trends or properties of these spline parameters. So we're going to use our NHANES example and see some properties of B-splines and natural cubic splines in our code. In this process, we'll examine just the general code to fit and evaluate these models, what happens if we change the degree of freedom or the number of knots, what happens if we change the polynomial degree within each set, and also we'll plot some confidence intervals or show that can be done. The first thing we want to do though is load the library splines so we can actually use that package to fit the B-spline and natural cubic splines. So here we just see some example code that specifies various definitions. So for example, at the top here, we see that the code for a linear regression model with both a B and a natural cubic spline looks quite similar from the splines package, with BS or NS being their respective functions. We see here in this case that we're defining the degree of freedom to be 4 in each model. Now, if you're fitting a B-spline, we can also further modify that degree of freedom. So here we see we're going to specify it to be 6 instead of the default of 3 or that cubic spline. It's worth noting that the NS assumes cubic polynomial terms with no degree argument because of that cubic spline intention. Now, once we fit these models, we can actually do very similar things that we've done to many of our other regression models. So we see down here in our bottom code chunk that we can, for example, fit our linear regression model with a spline. We can then create a new data frame object to, let's say, predict the outcome over the range of ages 6 to 80 in increments of 1. We can then save our predicted values to something like y_pred. And further, we can look at examples if we want to get a confidence interval. We can use the predict function and then specify an interval either for LM objects, confidence or predict, or for GLM, just the confidence intervals. Let's start by examining the B-spline and changing its degrees of freedom. Or in other words, looking at increasing the number of knots. Now, let's start with the simpler one with just 3 degrees of freedom. We see here that it has the solid red line is a fairly smooth fit over the range of our data. We do note that there is potentially some lack of fit or underfitting in certain spaces. For example, where I've drawn this arrow right now, around 10 to 20 or 15 to 20 years of age, it does appear to be overestimating the predicted SHBG for those ages. However, across the rest of the range, it doesn't look maybe as terrible, and it's definitely an improvement over just a standard linear regression. Now, as we increase the degrees of freedom, we do notice some other behavior. For example, in that same region here I've just circled, we see that by increasing the degree of freedom or number of knots by 1 to 4 here, or up to even as high as 20, we see all of those points are more flexibly modeling and actually better following the flow of our data. We then see if we move the circle forward just a little bit between 20 and 40, we do see a little bit of a differentiation depending on how many degrees of freedom we use. And then they again kind of converge in this next range between 40 to 60 before having a little more departures towards the end of tails as we get older. Now, what this suggests to me is that you can achieve very different performance by increasing your degrees of freedom, but you do want to be careful, A, to avoid overfitting, and B, essentially, if we see visually that 20 looks very similar maybe to 5, we might just want to go with a more parsimonious or simpler model with lower degrees of freedom. Another thing we can explore with our B-splines is changing that polynomial degree within each of our knot ranges. So if we use the default degree of freedom or number of knots, we can see what happens to the performance or fit by increasing or changing the polynomial degree. For example, if we assume a polynomial degree of 1, essentially meaning there is no polynomial trend within each group, or our red line here, which I've drawn an arrow to the right hand side to draw our attention to, we see that it doesn't fit the model very well still. Essentially, it just recreates our linear regression we had before. Now, we see though by setting a polynomial degree of 2, our green dashed line does a little better. It's a little hard to see with the color scheme, but it's better than the linear fit, but still probably underfitting the data, especially like we saw before. In this region of these younger ages, it seems to overestimate what the predicted value should be. Likewise, in the tail region, we actually see that it's starting to go off towards larger values in any of the other degrees of a polynomial. Now, as we increase to 3 or beyond, we actually start to see pretty similar performance where the values are largely overlapping with subtle differences, suggesting that maybe the default of 3 of the cubic terms are actually pretty good, but we could consider even higher degrees if we think they're necessary. It's also possible with B-splines to combine different polynomial degrees and degrees of freedom. On this graph, we now show examples where we have 1 degree of polynomial with either 3 or 10 degrees of freedom, and then a cubic or third degree order polynomial with, again, 3 or 10 degrees of freedom. We can see that the lowest sort of combination of 1 polynomial degree with 3 degrees of freedom is very similar almost to what we might think of as a segmented regression model. We see that in this case it goes down, hits an elbow, and then increases. But it has essentially linear trends in each region. Now, if we increase that number of knots or degrees of freedom from 3 to 10, we now see that the green dashed line has a bit more of a trend over the data. Likewise, if we increase the polynomial degree and then also our degrees of freedom in our blue colors, we see more flexibility, with the most flexible being our darker blue purple 3/10. But ultimately, again, your choice here will depend on the data you have and trying to find a combination that might fit the data best. Now, just briefly, we can look at an example of the plot of a natural cubic spline, and here just to illustrate plotting a confidence interval, just to get an idea of what this might look like in practice. Now, what we see here is that it looks like it's a fairly smooth, flexible trend over the range of our data, where it does appear to maybe be a little better behaved towards these tails. Again, because of that linearity constraint. We will note that in this figure, because of the extremely large data set we have, we are using a 99.99% confidence interval, which is highly, highly confident versus a 95% confidence interval even, just to illustrate to actually see some of the facts that in our plot here at each end and throughout, we have a nice smooth trend to those confidence intervals as well. In practice, especially with the smaller data sets, it probably is advantageous to also plot this confidence region or the confidence interval to get an idea of the variability as well over the range of your predictor X. So you might be wondering, how do I choose the optimal parameter for smoothing other than just eyeballing it? Well, we're not going to delve too deeply in this lecture in how to select the optimal parameter for smoothing, but different approaches have been proposed, and many of these have been talked about in more general cases for our class. For example, we've already seen you can use visual evaluation, basically seeing does it fit the data pretty well or not. More quantitatively, you might look at using model selection criterion like AIC, corrected AIC, BIC, and so forth to compare models with different parameters, where, as a reminder, you want to minimize your AIC. You can also use cross-validation approaches, abbreviated CV, by dividing your n data points into k groups or folds and then training and testing sets for evaluation. All these approaches could arrive at different conclusions, but ultimately it's up to us to look at the data to determine what might best fit and model that relationship. So as a brief summary of this lecture, splines provide a flexible approach to modeling nonlinear predictors that may appropriately account for their association with an outcome. Now, we saw that different parameters led to different fits, some of which could over or underfit data. In other words, suggesting we probably want to choose one of the other options. Now, there are tons of other types and approaches to splines that go well beyond the introduction here. So feel free to explore things like smoothing splines, penalized splines, and so forth to consider their own abilities to handle nonlinear data in different settings in your projects. There are also alternatives to splines that we'll discuss in other lectures, such as polynomial regression, or even that segmented or change point regression model I alluded to as well. Well, with that, I hope you enjoyed learning a bit more about the basics of splines in R, and I look forward to seeing you in a future lecture.